So I need to minimize this. Now, this looks like a slightly messy problem, right? Why? Because lambda 1 is in the denominator also, it's not a very nice function. So this is where, having a little bit more patience is required in working with the dual problem. How will I solve this? We solve this as though it's a new primal problem. So I have a function in two variables, lambda 1, lambda 2. Is there a constraint on this variable? Yes. So this simply means that lambda 1 greater than equal to 0, lambda 2 greater than equal to 0, right? So if you were faced with this as a fresh primal problem, what would you do? You would formulate its Lagrangian and then solve it using KKT conditions. So let's do that. So the new Lagrangian, let's call it W. This is going to be a function of lambdas and let's say mu. So mu are the new Lagrange multipliers of this problem, right? So what will I get? So I'm going to get, what is function minus lambda I Ci. What are the constraints in this problem? In terms, if I write in terms of C of lambda, what are the constraints? C1 of lambda is what? Lambda 1. C2 of lambda is lambda 2, right? So I'm going to write this whole expression, this is my f of x, minus mu 1 lambda 1 minus mu 2 lambda 2. This is the Lagrangian of the new problem, right? So this is going to be 1 plus 1 minus lambda 2 squared by 4 lambda 1 plus 8 lambda 1 plus 6 lambda 2. This is the first part, minus mu 1 lambda 1 minus mu 2 lambda 2. Okay, is there a constraint on mu 1 mu 2? Should be greater than equal to 0 because these are inequalities. So mu 1 greater than equal to 0, mu 2 greater than equal to 0. Okay, solve by the KKT theorem. Okay, so let's do that. So everyone's following what we're doing? We've got a second problem which needs to be taken care of, so we are taking care of it. Okay. So KKT will tell me what this Lagrangian, with respect to what variable will I minimize? Lambda, right? So this should be equal to 0. What do the complementarity conditions tell me? Mu 1, which is the Lagrange multiplier, multiplied by the constraint. What is the constraint? Lambda 1 should be equal to 0. Mu 2 into lambda 2 should be equal to 0. Okay. So let's, before we find this gradient, let's look at this. Lambda 1 equal to 0. Is it allowed? Actually, it's not going to be allowed because why? Because 1 by lambda 1 is there, right? So 1 by lambda, so therefore lambda 1 equal to 0 needs to be excluded from the domain of Q. So that's why lambda 1 equal to 0 is not allowed, right? So we'll just make a note over here. Lambda 1 equal to 0 not allowed in domain of Q. If lambda 1 equal to 0 is not allowed, therefore what is the implication for mu 1? Therefore mu 1 has to be 0. Okay. That's great because that will help me to make my Lagrangian solving a little bit easier. So what is this Lagrangian? So let's look at the expression you have for W and take a derivative with respect to lambda 1. What is the first term that you will get? Lambda 1 is only in the denominator, right? Yes, so I'll get a minus 1 by lambda squared. So this is going to be 1 plus 1 minus lambda 2 whole squared divided by minus 4 lambda 1 squared, okay, and 8, right? This is the derivative with respect to lambda 1. With respect to lambda 2, what am I going to get? I'm going to get a 2 1 minus lambda 2 divided by 4 lambda 1 plus 6, what else? Minus mu 2. This should be equal to 0 minus oh sorry correct okay and also mu2 lambda 2 equal to 0 right. So this mu2 lambda 2 again gives us two cases right. So two cases mu2 greater than 0 which implies that lambda 2 equal to 0 okay. So in this case what is my solution? So lambda 2 equal to 0 right. So what happens to the first term? 1 upon minus 4 lambda 1 squared plus 8 equal to 0 okay and anything left on the second term? Lambda 2 is equal to 0 so minus 2 by 4 so oh sorry that's the first term. The second term is going to give me what? Minus 2 by 4 lambda 1 so that's minus 1 by 2 lambda 1 plus 6 minus mu 2 equal to 0 right. So from the first expression do I get a value of lambda 1 right 1 by 4 does it and from here what value of mu 2 do I get? 4. Lambda 2 equal to 4 is it allowed? It's a Lagrange multiplier for the new problem. It was an inequality so it had to be greater than equal to 0 so it's allowed right. So this is legitimate okay. So this was easy enough to do. The second case is mu 2 equal to 0 okay. So if mu 2 equal to 0 what is the first expression giving me? If I take the gradient what am I going to get? Or I can just get lambda 2 directly from the second part of the gradient right. So what will I get? Lambda 2 minus 1 by 2 lambda 1 plus 6 equal to 0 because mu 2 equal to 0 okay. So that implies that lambda 2 is equal to 1 minus 12 lambda 1 okay. Now I can take this value of lambda 2 and substitute it. If you look at the first part of the gradient over here this is purely lambda 1 and lambda 2. I have got a relation for lambda 2 in terms of lambda 1. I can put it back inside it right. So yeah if lambda 1 is correct right. So we can stop at this one. Are we required to have lambda 1 lambda 2 greater than 0? Yes right. So this is showing us that we need not proceed further because any lambda 1 greater than 0 but actually no, what if lambda 1 is between 0 and 1 by 12? That's a possibility right. So we actually have to go ahead and solve it. So when you substitute this back I am going to spare you a couple of steps of algebra. What you get is this is the solution for lambda 1. So what is the lambda 1 that satisfies this? It's imaginary right. So obviously that is not feasible right. So this case mu 2 equal to 0 doesn't work. I am only left with mu 2 greater than 0 okay. So let's see, we didn't calculate so in this case 1 okay we already know lambda 2 right. So let's make a new page. So the only solution is lambda 1 lambda 2. What was the value of lambda 1? 1/4 and value of lambda 2 0 right. This is the only solution that works. So now Q of lambda, okay. What is Q of lambda? Let's look back at this. Where is our Q of lambda gone? This expression over here, this big expression over here. So in this I am going to substitute lambda 1 equal to 1 by 4, lambda 2 equal to 0, okay. So you can do it just mentally, because lambda 2 being 0 and lambda 1 being 1 by 4, what is the optimum value that you get? 4. Okay. There should not be a minus. Oh, sorry. Okay, very good. And we had a relation for x1, x2 in terms of lambda, right? If you go back, where did that go? Here is x1 star, x2 star, 1 by 2 lambda 1 and 1 minus lambda 2 by 2 lambda 1. So if I substitute 1 by 4 comma 0 in this, what do I get for x1 star? 2 comma 2, right? Okay. And if you recall, in our primal problem, what was our f star? Minus 4, and x1 star, x2 star was also equal to 2, 2, right? So this was the only KKT point that worked throughout, right? So here you have dual equal to primal, right? And that's not a surprise, because the objective function is the optimization problem is convex, so there is no duality gap. So this was just to give you an example in problem solving using the duality method, right? So you can see that there can be many solutions in between that will come because of the various cases that arise, but you have to eliminate them based on the step knowledge of the previous step. For example, domain of Q should exclude places where it blows up and so on. So that helps you to rule out. So if we just do a quick refresher of what we did, we took this very simple problem like this, minimizing minus x1 plus x2 with these constraints. We saw the solution graphically is correct, right? It's 2 comma 2, optimum value is minus 4. Then we took the dual problem formulation, objective function came as it is, which is here, and then I had the constraints over here. And to get to the Lagrangian dual, step 1 was to minimize the Lagrangian with respect to x, which I did over here, right? So taking gradients with respect to x1 and x2, I arrived at this relation between x and lambda. I substitute that back into the Lagrangian dual and I got one big expression for the Lagrangian dual. Fine. Then that allows us to move to step 2 of duality. Step 2 of duality is maximize the Lagrangian dual now. So I take this problem, solve the max problem. I did some algebra to convert the maximization into minimization, and this is the expression that I get. This in itself is an optimization problem, so I applied KKT and formed a new Lagrangian for this function. I called it W, and the Lagrange multipliers are mu1, mu2, right? So this is my f of x, this is my lambda I Ci, right? This is how we write the Lagrangian function, W equal to. So that's what I've done over here. F of x is as it is. I have my mu1 lambda 1, mu2 lambda 2. Okay, but with the constraints that mu1, mu2 have to be greater than or equal to 0 because we are dealing with inequalities. Okay, so we solve this by KKT, means setting derivative with respect to the variable, which is lambdas equal to 0. So with respect to lambda, I took the gradients and solved for it basically. We got some cases. In case 1, basically I got the solution which was correct. In case 2, I looked at something and gave me a wrong solution, right? So I eliminated it. Oh, we not only did we talk about lambdas being real, we in fact said they should be non-negative. Right? Why should lambdas be non-negative? Correct. So that condition is already there on lambda. So therefore, being complex is obviously also ruled out, right? Right? So that's how you would solve a problem using duality, right? Step by step. So it needs a little bit more patience because you're solving two optimization problems, right? So if the primal problem is easier, you solve that. If the dual problem is easier, you solve that. Okay. And you can always use some technology. CVX is a technology, right? Because it's an automated set of rules which does your problem solving and gives you the solution. So just as homework and for learning a new tool, go back and install the CVX toolbox on MATLAB or Python and try to solve this problem. You know, it will give you a lot of extra information. It will give you what is the duality gap, what is, you know, the Lagrange multipliers, the intermediate steps, you know. So it's also a nice way to see behind, you know, what is going on in solving these problems. Okay, but just keep in mind, if you start applying this to real world problems, it's very slow. So keep that in mind.
So when we say problem is convex optimization problem, convex, and all the constants, if they are convex, then we can directly say it is convex.
Correct, yeah, that is the definition of a convex optimization problem. Objective function is a convex function, constraint set is a convex set.
Instead of going for a constraint set, I see what are the constraint functions. If everything is convex, can I say it is convex?
Okay, that's a good question. So, supposing my constraints are convex functions, does that mean that the feasible set is a convex set? Say again? Correct, no, but the feasible set now is being defined by multiple convex functions. C1x greater than or equal to 0, C2x greater than, all of them are convex functions. Does it imply that the feasible x, is it? Okay, so let's take an example. Let's see if that always holds true. Okay, so let us say that I have C1x is equal to x2 greater than or equal to 0. Okay, C2x, let us say, is e to the x1. This is always greater than or equal to 0, right? So, no, that doesn't make sense. Okay. So, what if my, this is my convex function, right? And let us say my feasible set becomes this. Then, so this is my, let us say this is my C1x, and let us say that this is my C2x. Is it possible? So C2, so the intersection that I have here is not convex. But how will I define C2x? So the constraints have to be defined such that Cix greater than or equal to 0, right? So but C2 is not, right? So this is more like minus x squared, right? Greater than or equal to 0, right? So you're right. So if the functions are convex, then the intersection seems to be a convex. So this is not a good example because the constraint function, this is not convex. So you have a counter example where the C's are convex but the feasible set is not convex. Yeah, but considering a parabola is not enough because the constraint has to be that function greater than or equal to 0. Right? So if I take two parabolas, if I take this one and I take this one, to define and you're thinking of this being the feasible set, right? So one of the constraints will be concave, the other constraint will be convex. So it's not a counterexample, right? So this was, you're saying this was one of the tutorial problems, right? Intersection of convex. Hmm. Yeah, but here we're talking about functions.
So once the function is convex,
Hmm.
obviously its domain will be convex set.
No.
Convex
I can define a function f of x equal to x1 squared plus x2 squared, okay? But I am telling you that the domain is, this is my domain. It's up to me to define a domain, no? I say that this is the domain of the function. On this domain, the function is x1 squared plus x2 squared. So the domain is concave. I defined it to be so. But the function is convex. So I have a convex function on a concave domain, right? So it's not necessary that just because the function is concave, the domain has to be also convex.
When you say the constraint function is concave, then this will always be convex because we have greater than or equal to 0. So we want concavity so that we can use the bound. Like the function value will be greater than linear combination of individual function values, which is greater than 0. If it's concave, then the
If what is concave? The C's.
The C's are concave. Like in all the examples I took, I think it was concave.
Correct. Right. So if it's a so then intersection of concave functions is a it seems like it, right?
Because of the way you define.
Correct. Yeah. Let's look for a formal statement of this. I mean, because like this, just by arguing amongst ourselves, we can come up with some counter example. So I don't want to make a definitive statement. Maybe I'll post on Google Classroom what is the conclusive thing about it. Is convex, right? Convex function. Convex. Convex. Okay. He is talking intersection of the domains. You cannot intersect functions. You can intersect their domains. But I'll post a definitive answer for this. Okay.
So let's say the function, the objective function is convex. The constraint, okay, let's not worry about the constraint. Let's say the domain you are defining some non-convex, but
the domain of what?
The domain of this x1, x2. The feasible region. Yeah.
The feasible region is concave.
You are defining it like that.
Then it's not a convex optimization problem. Straight away.
You can still apply all these gradient techniques to get into the domain. So let's say for example the function is x1 square plus x2 square. And the
domain is concave. I mean, domain is non-convex.
Non-convex, but it's still like how it is a bounded domain. Like
Like this, huh?
We can still use gradient techniques to get these.
So you have to take care of the projection operation. So what we have defined in class is projection on convex sets. That's a well-defined operation. A projection on a non-convex set is, first of all, uniqueness is gone. So that is the tricky part. So then people may do tricks like expanding their domain to make it convex in a minimum way and then solving it and so on. Those are.
I saw in internet definition for a convex optimization problem is if all the constraints are convex functions.
Yeah, so I'll look it up and maybe there are other ways. There may be ways to define a convex set in ways other than this also. So we'll.
Analytically get the gradient and equal to 0. All we need to see is whether that point lies within the domain itself or not. At that point it doesn't become relevant whether the domain is convex or not.
If that point happened to be in the interior, that's fine. If you're in the interior of the domain, then the constraints are inactive. It's like a unconstrained optimization problem. In fact, this problem itself, the solution is 0, 0, which is the interior of the domain. So it doesn't matter what the domain set is. right? But if it is on the boundary, that may be the tricky part, right? Because that boundary point, how did it come? Did it get projected from somewhere else?
No, no, I'm not talking about the algorithm.
Hmm.
Let's say we know the objective function is convex.
Hmm.
What we need to find is like equally variable.
Hmm.
Analytically, we may not be able to do it for complex.
Okay. Let's say you solve it numerically.
Yeah, we solve it.
Fine. Hmm.
Get exponential satisfies.
Which is inside the set, strictly inside the set.
Like it belongs to the domain. It can be on the boundary of the domain.
Hmm.
Only the domain.
Hmm.
There's no
Hmm. Hmm.
constraint.
Hmm.
That's all we need to do.
Then you're done.
Well, you know, whether the domain is convex or convex.
Yeah, but I doubt these things happen very often in real life.